One of the most common questions my coaching clients ask me is, what are C++ pointers, where to use them, and how to use them? In audio programming, the topic of pointers comes up quite often because in audio code we need to deal with C-style APIs. For example, here you can see that Juice's audio I/O device callback has this audio device I/O callback with context. So it's a function that we need to override if we want to receive input samples or we want to output samples. So exactly, it's crucial for audio programmers to understand what are pointers and how to use them, and we'll explain it thoroughly in this one video. Hi everyone, this is Jan Wilczek from WolfSound.com, and if you're new to this channel, here you can learn how to process sound using self-written software. And indeed, for self-written audio software, pointers are incredibly important. So to kind of facilitate the understanding of pointers, I've put together this article. And as you can see, it's quite long and it has a lot of moving parts. That's because, in general, pointers, it's not an easy topic, although it should be. And it's often misunderstood and pointers are often misused. So in this video, I would like to have a kind of a stroll along these topics, and we can discuss various aspects of pointer programming. So be sure to check out the full article, the references in the description below. And now let's start by discussing what actually are pointers. So in its core, pointer is actually a variable that stores and possibly an address in memory. So when we type some variable, we can take the address of this variable, right? So we can address of x, and this is the address of operator, and we just taken the address of x. So this is a variable, and this is also a variable. We call this variable a pointer because it is of a pointer type. So it has this asterisk here. And this variable address of x has a value which is equal to the address of variable x. So we can output these values. And for this, of course, I need the IOStream header. Okay, and as you can see, x is 1 as expected, but as the address of x is some hexadecimal number, which is the address in memory where this x lives. And that's the basic understanding of pointers. By the way, if you're curious, what I'm using here, it's the compiler explorer, which you can find on the godbolt.org, which is an incredible tool to compare various C++ compilers and also test various compilation scenarios. So that's not the only use of pointers, obviously, because otherwise this topic would be already closed. So another application of pointers is that pointers can also be used to point to an array in memory. So if we have a static array, so array whose size is known at compile time, so here I say that it's 4, I can create it like this. I need to remember to put here 5 elements. And this array, although it is of the array type, right? We could say so, but the truth is that it's implicitly convertible to pointers. So we can have something like this, and we can take the address of the first element, And we can now print out the first element. And we can also print out the array itself, and we can also print out the address of the first element. And what turns out, it's the same thing. And that's because an array type, a plain C-style array type, is implicitly convertible to the pointer type. And thanks to this fact, I can also use array semantics on the pointer, so this will also return 1. So this may already seem a little bit complicated, but yeah, that's kind of a quirks of the C language, and C++ inherited it. So remember, an array type, so the type and the square bracket is implicitly convertible to the pointer type. And here's a good point, a good moment to show another thing that's maybe not so nice that is possible with this syntax. So what we can do when we have an array, we can of course assign elements to it, right? But the problem is that it has 4 elements, so it's index 0, 1, 2, 3, right? But if I access the value at index number 4, I get no compiler warning. And this actually compiles and this runs even if I add all warnings. No, I just get an unused variable warning, and that's it. And although it's static array, so its size is known at compile time. So it's said that, okay. We can ignore this one, but maybe if I do something like this. Okay, yeah, now it doesn't complain, but still, this is what is called undefined behavior in C++, because I'm accessing memory that doesn't belong to me. I'm accessing some point in memory, some place in memory that does not belong to me. It's outside of the range of this array. And in C++, in Java, in C#, in Python, you would get an out of range exception, right, when you do so. But in C++, you get nothing, basically. But at the same time, it's undefined behavior. So as soon as this happens, all the bets are off, and you cannot guarantee a correct behavior of your program. So that's a very sad thing. And as you can see, it's very easy to do this, right? You just, access one past the last element, and the damage is already done. So how we can mitigate this? We can mitigate this by using std array. And that's the recommended way to use arrays. In C++. So now we get the same semantics, but we already know the size of the array. So I can now print out array.size. So before, like this raw pointer did not tell me anything about the size. I needed to remember the size on my own. What's the size of that array? But here I can specify this as a template argument, and I have access to the size. Unfortunately, we still can access the array out of its range. That's because C++ assumes that we are grown-ups and we know what we're doing. But with an array, we can use the add accessor function, and now we get an exception and segmentation fault. And this add variant of the container, of the C++ containers, is a checking variant. So this square brackets operator does not check if it's within range, but the add variant does check and throw an exception if we are accessing value out of range. Last thing that's important about this std array, we can access the address of the first element as we could, but we can also see that, okay, so now I'm printing the address of the first element, but it doesn't have to be some cumbersome. We also have a data member, and this data is basically again of the pointer type, right? So that's how we can go back to the old notation, but still std array is nicer because it remembers its size. And with, you know, this C style plain arrays, which we had in the beginning, we need to remember the size on our own. Okay, but now what will happen if we don't know the size of our arrays at compile time, right? Then we'll deal with so-called dynamic arrays. And dynamic arrays means that we need to dynamically allocate memory at runtime. So this is a dynamic array. And here we say, okay, we want to allocate 4 floats, and this happens at runtime. And these elements are allocated on the heap. So once again, this is allocated on the stack. So stack is the place where all the memory whose size is known at compile time resides, and this is allocated on the heap, so place in the process's memory where we can allocate new memory. Okay, so yeah, and the thing is that this number cannot be some variable. Okay, so basically this number has to be known at compile time, but this number can be anything. So it can be a result of some computations, it can be a result of a user's choice, and it can change later, right? And in audio, we typically deal with an array of samples of type float. And these arrays can be of different size depending on the setup of the audio card. So it can be 96 samples, 128 samples, 256 samples, and so on. So once again, we need to allocate memory, but the caveat here is that now, once we have allocated this memory, we need to free it, because otherwise we'll get a memory leak. So obviously, this is a very short program, and when this program exits here, then this memory is free because the process memory is freed. But in a average program that you will work on, it's typically not the case. So this program typically runs for some longer time, and there you need to always remember to deallocate your memory, because as soon, let's say this is in a function, and if we call this function from main, and this line is not executed, right? Then we get a memory leak because we don't have access to this dynamically allocated memory, but we have never freed it, so we can never use it again. And in programs that have memory leaks, typically what happens is the RAM usage increases over time, and as a result, the user gets angry because they don't have as much RAM to use as they had. But also, you run into the risk of not being able to allocate any new memory. So you need to always remember, right? And people say, okay, it's not a problem. So I allocate memory, then I free it. So what's the big deal, right? The thing is that there are a few problems regarding to it. The first problem is something I experience a lot, that when you have two things to remember, right? To allocate memory and then to deallocate it, you typically allocate memory and then forget about deallocating it. And in a large program, it's very likely to happen. But it's not only this. It may happen that, for example, if you have an early return, right, from your function. So if you say, okay, if the work has already been done, then we just return, right? And which means that if we have an early return, this line will never be executed, right? Of course, you can go here, paste it, right? But yeah, it's very cumbersome to remember all this. But it can be even worse, right? We can have a situation where an exception is thrown, right? If we throw an exception, this line also won't be executed. So also when we use other functions that may throw exceptions, we have no control over the fact that this line won't be executed. So the question is how to overcome this. Well, it's a typical advice that I always give is don't use pointers. And when you use dynamic memory, always use the standard way to do it. So, okay, it's a dynamic array, but a dynamic array is nothing more fancy than an std vector, right? So that's an std vector. Now we don't have any dynamic arrays. And std vector, which is in the header vector, it allocates memory on its own. It can be resized automatically. And if it's destroyed, like upon this return or upon throwing this exception, then it automatically frees the memory in its destructor. So really, when you deal with dynamic arrays, there's no reason not to use vectors. So there is maybe some edge case when you need your memory to be aligned very specifically, but I believe that since C++17, it's already possible to have vector, align your data as you wish. But if you're interested in it, I also have an article and a video on how to properly how to use vectors with dynamic memory allocation, or how to have vector-like features. So if you're interested, you can check it out. Also, there's a link to it in the article. So that's typical thing. For static arrays, use std array. For dynamic arrays, use std vector, and you'll be fine in most of the cases. Okay, but we can allocate also more than just arrays, right? We can also allocate objects. And I can allocate objects like this, right? So here I allocated memory needed for just one float. And then I can dereference it. So that's this operation. This asterisk is the dereferencing operator. So I use it to access the variable that the pointer points to, right? I'm not changing the pointer, I'm changing the variable that the pointer points to. And I can print out the address in memory. And I can also print out the variable. And of course, what we have forgotten to do, right, is to deallocate this memory. So now this variable lives on the heap. It doesn't live on the stack. Okay, and now the question comes up, why would I like to use dynamically allocated objects? And in the article, I discussed this. So we are here. So if we have a large object, that's also something to better to allocate on the heap, not to overflow the stack. if we want to use polymorphism, so we want to manipulate the derived class through a pointer to its base class, we want to indicate that the variable may be missing, although here maybe stud optional would be a better choice. If we want to, create an object in one scope, like in a function that we had, but then we want to use it in a different scope, so we want to pass it somewhere else. Exactly, so if we want to pass an object to a function, for example, without copying it, we can pass the pointer. If for some reason we cannot use a reference, but actually for polymorphism and this scenario, it's always better to use a reference. Sometimes there's also the pimple idiom, some pointer to implementation. It's a kind of advanced technique to reduce the compilation time and hide implementation details, but it also uses pointers. But then again, there are maybe better ways to do it. And of course, if we need to interact with C code from C++, that typically also use pointers. But in all these scenarios, please try to avoid pointers, mainly because of the problems with deallocation. So here is a quick example of how it could look. We have some large class, there's a lot of large members, some arrays, etc. And then we can allocate it as we've shown, and then we can free this memory. But the same thing is with dynamically allocated members, is that we can always forget to deallocate them. So let me bring this example once again. So we have some large class, and we want to allocate it, and then we need to deallocate it. Okay, so is there a better way to do this? Of course there is. We should use the unique pointer or the shared pointer. They are in header memory. And then you go std unique pointer, large class, let's see, std make unique class. And now we don't need to do anything else. When LC goes out of scope, this will be automatically freed. So no memory leak. This is also exception safe. So if large class constructor throws an exception, make unique will also handle it. And now you have also a make shared. So you can also do this like shared. And what's the difference between them? It's not in the scope of this video, but please in mind that these are the preferred ways to use dynamically allocated objects. And now let's briefly go to how it looks in audio programming. So in audio programming, for example, in the Juice C++ framework, you also use dynamically allocated objects exactly for the reason of outliving its scope. But maybe the more important one is to have the polymorphic behavior. So here you can see that in the plugin processor, there is the function called create plugin filter. And from this function, you need to return an instance of your plugin processor. And then Juice framework, it doesn't know what type your audio processor is because it manipulates it only through this audio processor pointer. And of course, in audio programming, we often get an array of samples exactly using a pointer. So as you can see in this example, we want to apply some gain to an array of samples. So we obtain the array of samples and how many samples there are to process. And for each of the samples, we multiply it by gain. And what's nice about this, we can use here dynamically allocated memory. We can use here statically allocated memory. So array whose size is known at compile time, but we don't care, right? We just access these samples, but still there's a better way to do it. And I will show you this later. Okay, so now let's go to the null pointer. Null pointer is a way to say, okay, I don't want this memory block, this pointer to point anywhere, right? So a null pointer is a very special value. It's of a dedicated type called null pointer t. And that is because in the C language, typically what you could do is you could do something like this. I don't know if I need something more. Okay, no, it does compile. So this is null, but if you print it out, it prints 0. And if you print null pointer, it prints null pointer. And that's the difference, because actually null was a C macro for the value of 0. So it was simple int, right? But no address in memory is not 0, right? It simply means no address in memory. So C++ improved upon it. We get the null pointer. And what's also nice about null pointer, if I now try to, whoops, dereference this pointer, the program terminates with an error. So we get segmentation fault, and that's very likely so. So the idea is that if we point to some memory that doesn't belong to us, we can dereference it and then we get undefined behavior. But if we dereference a null pointer, then our program simply crashes. And that's in some circumstances that maybe a more preferred behavior than undefined behavior when we really don't know what will happen afterwards. I mean, all bets are off. Okay, so we have our pointer, which can point nowhere. How we check if it points somewhere? So of course we can compare it to the null pointer. So here it should be it says that pointer points somewhere. It's not a null pointer, so we should be able, in theory, be able to use it. We can simplify it also like this, so we can just write if pointer, and it has the same meaning as before. So the problem, of course, is that if pointer points somewhere which is invalid address, but an address that does not belong to us, we still get undefined behavior when we dereference it. So that's why often you can find such code that you allocate some memory, but this is typically in older programs. So then you delete this memory, and then you set the pointer to null pointer. And that this will indicate to other programmers that, okay, we point nowhere, this pointer should not be, dereferenced, it should not be deleted, etc. Because if we now try to delete this pointer, what we get is we get basically nothing. But if we did not have this, then we would get a segmentation fault, because double delete creates a segmentation fault. So again, this can all be avoided if we use make unique, make shared, std vector, std array. And that's always, or maybe I should say std vector and unique pointers and shared pointers for dynamically allocated memory, because they handle memory management in their constructors, destructors, and member functions. And we don't need to remember to explicitly free this memory using delete. Okay, let's move to another topic, which is very interesting to a lot of people who are new to programming. That is the topic of void star. And people ask, okay, what is void star? People know void from functions which return nothing, right? If I type in return or I remove this line altogether, this function does not return anything. But what is void star then? Well, void star is basically a pointer to a raw memory block. So I can do something like raw memory pointer. the thing is that I cannot use this memory on its own. And well, where does it come from? Because with new, we would need to allocate a specific type, but typically it comes from the C language when we had the malloc function also for allocating memory. So in C language, we would do something like this. We'd call malloc and then 4 times the size of a float, which is basically if we want to allocate 4 floats. And now how to use it? Well, we need to cast it to the appropriate type. So we would do something like we do something like this in C++. It's called reinterpret cast, and we say, okay, we want to treat it as an array of floats, and now we can simply access it. Of course, I don't have to remind you that this is error prone. So one thing which we already forgot to do is okay to deallocate this memory. And I remind you that you can do it only once. So if you free raw memory pointer, you cannot free it twice, but you also cannot free this piece of memory. It's also malformed. So remember, when you allocate memory, you can only free it once. Okay, so that's one caveat. Another thing you need to again remember was the size of it. And then you need to do this manual casting. So there are all sorts of problems with it. And but yeah, sometimes you need to do it, right? If you interact with some C code or C style code. And what's the use case for it? I think the most common use case for this kind of thing is to avoid giving a specific type in any function call. So you want to pass some data to a function, but you don't want to be explicit about what its type. You want to hide this type information. In C++, there is a kind of a hot topic which is called type erasure. I won't go into it, but it also uses this technique a little bit in the sense that it hides the information of what the actual type of a variable is. But in audio, I think most often meet it when we use callbacks. And here I have an example from OpenSLES, which is the sound library which was previously recommended to use on Android. So it's a kind of also a like low-level API. And as you can see, for example, you can register a callback, so a function that will be called when you're playing back sound. And this function should have this kind of signature. So it should have 3 arguments. The first one is the interface that calls you. The second one is the context, so this raw memory block. And the third one is the actual event that happened. I think it's kind of an enum. And when you register the callback, then you pass the interface that's responsible for registering this callback. So basically, it's a kind of a convoluted way to call an interface method. So on this play interface, we call register callback. Then we pass it the callback itself. So a function with this kind of signature, or and then you can pass it a context. So some piece of memory that you know the significance of, but OpenSL, it doesn't care. It will simply give it back to you in the callback. So how does it work? Here I have an example. So you can check out the full specification here. It's open online, but it's, there's no syntax highlighting. But if you want to go through it, then please, you have parts of the example that I posted in the article. There's a link to it also in the article. So yeah, how this could look. We have some class, right? We have some class that's called playback event handler, and we want to change this free function callback into actual class interaction, right? So we want to escape as soon as we can from the free function into the domain of objects. So we have this actual handler, something that we want to handle our event with, and but we need a free function, a callback, right? So here's our free function, which has the signature that I described to you a while ago. And here what we do, as you can see, we cast the context, so this raw memory block, to a pointer to this event handler, right? Here could be, and then I use this handler to handle this play event. So I call a function on this play event handler. And this arrow operator is simply a shorthand. So if you have a pointer, you can call the function of an object this pointer points to by writing pointer, arrow, and then function name, and then, you know, the typical arguments. This is an alternative to writing something like this. So to dereferencing first, and then using the dot operator. Okay, so here I handle the event using an instance of my playback event handler class. And now how to register this handler. So I create it first somewhere, and it needs to live there as long as this callback is called. And then I'm registering this callback. So as you can see, I register callback, I pass the instance of the play interface. Then I pass the play event callback, so this function, the pointer to this function, and then I pass in a pointer to my handler, which I cast to void star, so to raw memory. So again, OpenSL doesn't care what I pass here because it will simply give it back to me in the callback. So I can pass here additional data that has meaning just to me as a programmer, and I can then retrieve the pointer to the handler in the callback and redirect the control flow out of the free function. C++ pointers is one of the topics that you need to master if you want to become an audio plugin developer. If you are interested what other skills from C++ and other areas of computer science are needed to be an audio developer, be sure to check out my free audio plugin developer checklist. There I list every bit of knowledge that I believe is important if you want to become an audio plugin developer. So head over to thewolfsound.com/checklist to cross-check your knowledge against what's needed in the audio industry. Next thing in the list of our pointer topics is the double pointer. So again, people see something like this, and they're like, okay, what is it? What is it, like a double pointer? What is it? So there are a few things it can mean. So one thing, which I have not seen quite often, but yeah, it also happens. So you have some variable, and then you have pointer to x. So you take the address of x, and then you have pointer to x, which is the address of pointer to x. So this is a kind of a recursion. You can also do it with 3 asterisks, but yeah, it would be like a programming hell. I've never seen 3 stars in practice, 3 asterisks. And what's the usage for this? Well, again, in the C days, you would have something like this. Because you did not have references, right? So in such a function, you would do something like this. And then in your, let's say, client code, you would go, okay, I have a pointer, and then allocate, pass in the address of pointer. And of course, we need to remember to delete it then. So here's it's kind of a reference thing, right? In C++, you wouldn't do something like this, you would do something like this. So we would pass in a reference to the pointer, which looks, again, a little bit weird, but it's nicer than, it's nicer than this notation, because, of course, pointer can be null, right? And you need to handle it again, like if pointer, then execute this code. Yeah, and otherwise do nothing, throw an exception, you don't know. So yeah, that's why we should avoid using pointers. Okay, but float start star can also mean a different thing, right? It can also be an array of pointers. And that's a typical application in audio. So we would call it array of arrays. And we allocate a 2-element array of pointers to floats. Then what we need to do is we need to allocate the first array, and let's say it's 2 elements, and then we allocate a second array and it's 3 elements, which is already very cumbersome, and then we can fill it. So we use double indexing here, so this is 1, and this is, I need to remember all of the dimensions of this array. So the first dimension has just 2, is of size 2, and the second dimension is different depending on the array. So the first one has 2, and this one has, I think, 3. So, whoops. Okay, so that's how you fill all the possible entries in this array. And now you need to delete it, right? So what you do, you need to delete, you need to free the first array. You need to free the second array. And finally, you need to free the array itself. So this is very cumbersome. And the thing is that if this allocation fails, then we get a memory leak again. So this is really, really cumbersome. And maybe it's a good place to, say that if you fail to allocate memory, then this std-alloc exception can be thrown. So I have not seen it handled in code quite often, but I did see it happen, and it can exactly happen when you have memory leaks and you fill up the RAM and the operating system says, okay, here's the hard limit, you cannot allocate more memory, and it simply throws an exception here. But, this float star is actually used extensively in audio processing because it's used in audio callbacks. And here I have an example for you. So an audio callback is a kind of a thing, as you saw earlier for playback events, but in Juice you can also have this if you want to manipulate the input samples or manipulate the output samples. So here you can see that if you want to process samples in a standalone audio application using Juice, you need to create a class that inherits from audio IO device callback, and it overrides 3 methods. And one of them is this audio device IO callback with context. And here you can see that I have input samples, I have the number of input channels, so the first dimension of this array. Then I have the output samples and the number of output channels, so the first dimension of this array, and the number of samples, so the second dimension of both these arrays, how many samples there are in each channel. And then I have some additional information. So what is nice here is that Juice immediately, escapes this double asterisk notation. It creates their own audio buffer. And as you can see, it removed the const from the input channel data, which is interesting, but that's what you sometimes need to do. But here's exactly the case where we pass in a 2-dimensional array. So here I have an example. Here's how you can iterate over input channels and over the input samples from the input channel. And the same you can do for the output channels. And you can access each of the output channel samples. And you can register this callback. Here's also a nice example. So you initialize the audio manager with a number of input channels, with number of output channels, and then, you know, the remaining arguments, which you can ignore. And then you register the audio callback as you did. So you pass in the address of the callback that you have. So this is a class instance, and you pass the address of this class instance to the device manager. And it then will call exactly this callback every few milliseconds, right? Regarding how your audio thread is timed and the number of samples you requested. Okay, and what you can also observe is we don't have just float star star as a two-dimensional array, but we have all these consts here, right? So in this context, we can see it well here. So when we have this kind of thing, which can be very confusing to people not well versed in C++, and it frankly is also confusing to me, what I typically advise is to read it from right to left. So it's a pointer to const pointers to const floats. So this pointer can itself be changed, but the array of pointers it points to cannot be changed. And also the samples in these arrays cannot be changed. And it makes sense, right? Because when you get input data, and this will be, you know, called to all the callbacks, you don't want to be able to change these samples, right? You don't want to be able to mess up with these samples for other callbacks to get called. But for the output samples, it's not the case. So we have a pointer to const pointers, right? To const pointers. And it's again nice because we don't want to change the pointers to the output channels. I would see no use case in this, but the samples themselves are mutable, right? We can change the samples. So again, it's a pointer to const pointers to floats, which are mutable. And that's why we can modify the output channel data, and that's why we cannot modify the input channel data. And that's all well thought, but it can be confusing. So typically in programming, you know, const means that if you have a variable and you declare it const, it cannot be then changed. So you cannot then reassign it to 0. And also if you have a class and its instance is immutable, then you cannot call members which change the state of this class. So if in this example, I cannot call setBar because bar changes the member variable mbar. So this is not a const function. So this instant would be changed and it would break the const contract. So that's the typical meaning of const, but with these pointers, it can be, you know, really misleading. So what I did, I put together a huge table, right? And here you can see what each of these mean. So we have a pointer to float, you have a pointer to const float, you have again a pointer to const float, you have a const pointer to non-const float, and so on and so on. And remember always that when you have a pointer, it can point to a single float or to a single object, it can point to an array of objects. And when you have 2 dimensions, then, you know, it again expands. So we can have a pointer to an array of pointers to other objects or pointers to arrays. It can get really messy. So that's why I always say don't use pointers, right? So avoid pointers at all costs. If, however, you need to deal with these kind of APIs, this table should help you. I explained here, you know, every possible meaning. And then I also included here an example on Compiler Explorer. Here it is. So you can see that you have an array test, you pass in the array, and then you also use this notation and you see what is possible and what is not possible. And I also do it for a multi-dimensional array. So here you can experiment with all these const floats, asterisks, and whatnot. So have fun doing this. One more tip I can give you to better understand pointers in C++ is to subscribe to this channel, like this video, and turn on notifications, because apparently it really helps with understanding pointers in C++. I don't know why, but it really helps. Trust me on this. So while I was writing the code for the examples regarding the two-dimensional array, I ran into this error, right? So you try to assign the two-dimensional array, so of mutable pointer, to an array of mutable pointers, to an array of mutable floats, to an array of mutable pointers to immutable floats. And this fortunately doesn't compile. So it says invalid conversion from float star star to const float star star. And why isn't it possible? Well, let's consider the following example, which, by the way, is taken from the frequently asked questions of the ISO C++ standards committee. So let's say we have a constant float x, and we have some pointer p, and now we assign, we create some other pointer to pointer q that takes the address of p. So, and here we get an error, so we cannot convert from float star star, because, you know, the address of an address is of type float star star. We cannot convert float star star to const float star star. And why cannot we do this? So let's say that we could, and now we can write the following code. So we mutate the pointer that the q points to the address of x, right? And we can do this because x is a const float and q is a pointer to const float. So we mutate the pointer to const float through q. And now what we do, we assign the value, the value to which p points. So we change it to 0 floats. But what's the logic behind it? Well, p suddenly is capable of changing the float it points to. So p is a pointer to a mutable float. So we can obviously change the value of the float that p points to. And if the conversion from float star star to const float star star was possible, we could change p through q so that it points to a const float, but p doesn't know that it's a const float, so it would allow the value it points to be changed. So in this way, we would kind of remove the const requirement. And of course, it would break the whole contract here because we want to have x, which is immutable. So that's why we cannot cast float star star to const float star star. I encourage you to run this example on your own and study it on your own because it's really interesting. It's really quirky, and I didn't know about this before I started working on this article and this video. The last point I would like to mention is what we can do about callbacks that, you know, look like this. Process samples, it's floor star samples, and then it's samples count. So such a callback is all over audio programming. So here, what then happens, typically do something like this. We have a for loop. And we modify each sample. So in this case, we silence it, right? So what is the problem with this code? So one thing, now there are a few problems. So one thing is that information about the array and the number of samples it holds is decoupled. And every time in programming where we have two pieces of information that belong together but are passed separately, this is really error prone. So this typically gets misused. This function is now prone to be called with invalid arguments. So how could this look like? So for example, samples could be null, right? But samples count could be non-zero. So we could write something like this: null pointer and 2, right? So now this should crash because we're accessing a null pointer. And you're saying, okay, I would never pass something like this. But of course, in real code, you would have something like this. And here you would pass p. So you wouldn't even know that p is a null pointer in your particular example. So we'll get a segmentation fault. So you would need to check here is float star is null. And obviously, Murphy's law says that whatever can happen will happen. So this is quite error prone and risky. Another thing is that samples count could be off. So we could have something like float p of 2 is equal to 0f, right? But here we say, okay, it's 3. And now it's even worse because we get undefined behavior. We don't get a crash. We're accessing some memory that doesn't belong to us here. So it's really, really error prone. So why does this happen in the first place? This was typically used because such a function signature allows us to treat dynamically allocated memory and statically allocated memory in a unified way. So when you have array of, let's call it dynamic samples, and we can make it again of size 4, filled with ones, and we have array float 4, and again here we have something like this. So we have two arrays with samples. One is dynamic, other is static. And yeah, of course, for this we need to again include vector and array. Okay, and now we can process dynamic samples, and like this. We need the pointer to the underlying data. Okay, and we can do the same with static samples. So you can see that I can use one function signature to process both these arrays in the same way. You could say that, okay, in C++ we have iterators, and that's fact, we could use iterators here, but the problem with iterators here that they are not indexed. And in audio, we often need this I index to access a particular sample or to have a delay. So that's why this function signature is used. But what is, of course, also possible here, we can do this thing, and that's not really, not nice if you ask me, but yeah, what can you do about it? Well, it turns out that since C++20, we can do something about it, and we can do this without any runtime or memory overhead, or at least with a minimal one, but a one that can be easily optimized by the compiler. And what I mean by this is span. So from C++20, we got std span, and now we can rewrite this function to be a span over our samples. And it allows us to treat samples in a unified way. So as you can see, it doesn't compile, and that's because I need to specify that I want to have C++20. Okay. And now it complains that I don't have samples count. And that's why, because now this span holds not only the samples, but also the size of them. So that's really, really cool. Of course, now this is a signed unsigned comparison, so I need to make this unsigned, and the warning goes away. So how do we call this thing? So we can call it in multiple ways. So one awesome way to call it is simply like this and like this. What we can do, we can keep the previous call and just, have this kind of an initializer here, which will create the span for us. So that's nice. If we have a pointer and the size, we can always convert it to span. The best thing about this is that we cannot do something like this. So this doesn't work because we cannot create a span from this type null pointer t, right? Even if I type here std span float, right? It says there's no matching function call to std span float with null pointer t. So it doesn't work. And that's really, really nice. This allows us to treat samples in a unified way in this function. And I would say this is the recommended way to use in C++20. And if you cannot use C++20, then you can go to some, let's say, Google browser, and you can say, okay, let's say span pre C++20, and perfect. You go to GitHub and you have an implementation of C++20's std span for older compilers, which you can readily use. So that's how to circumvent this. What is also nice about this is another cool thing, that when we have a span, we can now simply iterate over samples like this using the for each loop. And that's, even a simpler syntax, less error prone. And that's something that we couldn't do with this float star and the size before. So use std span. Really, there's no performance cost about it, no slowdown of your software. This float star thing is not more performant in any way. So just use std span. Okay, so this was a very long video, but I believe that we cannot discuss pointers in a short video. And I really wanted to show various use cases, various contexts where pointers come up. So as a brief summary, in C++, in a pointer to type t has, maybe I can show it here as a summary. A pointer to type t has type t star. T star can point to an instance of t or to an array of t's, so that's unfortunate a little bit. Then we have t star star, which can point to a pointer to t, or can be a pointer to an array of t's, or can be a pointer to an array of pointers to t's, or a pointer to an array of pointers to arrays of t. So you really need to remember what is which, unfortunately. Then we have the null pointer, which means that we cannot dereference this pointer and it points nowhere. Then when we allocate memory on the heap dynamically, we must always free it, otherwise we have a memory leak. We should always prefer stack allocated variables, so normal like local variables like this. This is a stack variable, dynamic variables. And then we should use std array, std vector for arrays, not manually allocate memory, not use C-style arrays. Then we should not use naked new or naked delete. We should use unique pointer, shared pointer with make shared and make unique. Then if we interact with some C-style API, this is one thing that I have not maybe shown in a lot of detail, but we typically can use C++ destructors to deallocate memory. So if you're allocating really some raw memory or you get it from a library, then always make sure to wrap it in a class, because the destructor of a C++ class is always guaranteed to be called. And in this way, this memory will always be freed, even if an exception is thrown, an early return occurs, and so on. Use std span to treat ranges of samples in a unified way, or ranges of objects. And then again, if you interact with some C-style APIs, use std span or wrap it in some kind of class that will free the memory in its destructor. So that was it. I hope you found it useful. If you're interested in more of this C++ audio stuff, be sure to leave a like and subscribe to the channel, turn on notifications. And if you're interested which other parts of C++ are relevant for audio programming, head over to thewolfsound.com/checklist and check the points on my audio plugin developer checklist that are relevant for C++ programming. Once again, thank you for watching and see you in the next one. Take care.